as we move into the home stretch, this will be chapter 9, section 1. This gets into what we call correlation. So a correlation is going to be a relationship between two variables. The data can be represented by ordered pairs, where X is going to be the independent variable and Y is the dependent variable. So if you look down here, these are going to be what we're going to be kind of getting into is graphing, scatter plots. So this takes us back a little bit. So in this section, we're looking for what's called a linear correlation. So we're looking for, does the data kind of spread out and kind of make a line pattern? So this first example, this would be considered a negative linear correlation. Notice as X is increasing, as X, remember this is your X and Y axes here. So as X is increasing, notice that your graph, your Y values are getting smaller and smaller. Your graph is going in a downward motion. So if it's going in a downward motion, then that means it's kind of decreasing in the Y's. So as you go to the right, notice that the graph is going in an upward direction. So as X's are increasing, Y tends to increase. This is considered a positive linear correlation. So when the data is everywhere like this is considered a no correlation at all. And this has some type of pattern, but right now we're dealing with linear. This does not form a linear correlation. So mainly what we're looking for are negative linear correlations and positive linear correlations. So we're going to be starting out with just plotting some data and see if there's some type of relationship in the data, which we'll call a correlation. So here would be the first example, constructing a scatter plot. So an economist wants to determine whether there is a linear relationship between a country's gross domestic product and carbon dioxide emissions. The data are shown in the table at the left. Display the data at a scatter plot and describe the type of correlation. So we'll need our calculator. So I'm going to slide this over. Get this back up. Maybe slide this back over a little bit. Make this a little bit bigger so we can see the data. Get me out of the way. So what we're going to try to figure out is, countries with big spending, do they have a lot of CO2 emissions? And right now, my prediction would be, yeah, because, United States and China have big money, and they also seem to create a lot of the CO2 emissions in the air. But let's see what the data plays out here. So I'll pause. Well, before I pause, I'll show you how to get to that again. So we hit the stat button, and we use number 1 for edit. And if you have to clear your data up, you go up to L1, and there's nothing there. So another thing I guess I need to bridge to you is, how do you turn a stat plot back on? If yours isn't turned on, stat plot is going to be, let's see here. Let me quit this here. Stat plot is going to be, you have to hit the second button and the Y equals button, and the stat plot's over here. So number 1, I'm going to hit enter there. And right now my plot's turned off, so I have to hit enter again to turn it on. And the type of scatter plot, remember how we did these in different ones? We were doing like histograms back earlier on. So yours may be still on histogram. So we need to move it back over to this first one that looks kind of more like a scatter plot. Hit enter. X list is going to be L1, Y list is going to be L2, and everything else looks just fine there. So we'll quit that. Yeah, so make sure our stat plot is turned on, and then we can go to stat, edit, and this is where we put some data in. So I'll pause my video for a second and see if I can get my data in here. So I've got my data entered into the calculator. This is where you have to kind of be, patient. Notice how the X's is the gross domestic product in trillions of dollars. That's your independent variables. And then the CO2 emissions in millions of metric tons is going to be your Y variable. So we have this data. Now to graph it, what we do is we hit zoom, and it's number 9. See, it says zoom stat, hit enter there. And that'll create our stat plot. So that's what our stat plot's going to look like. So notice how it does have a little bit of a positive linear correlation. So it kind of has a little bit of a pattern here of a positive linear correlation. As the x's increase, the CO2 emissions or the Y values increased. So it's kind of what we're picking up on there. Okay, so let's see what we have next here. So the next example is construct a scatter plot. And this time we have students conduct a study to determine whether there's a linear relationship between the number of hours a student exercises each week and the student's grade point average. The data are shown below. Display the data in a scatter plot and use to describe the type of correlation. Okay, so to do this, again, I'm going to get my calculator back out here. I don't want to necessarily erase all this data just yet. So under stat plot, I'm going to turn on a plot 2 and see what that does. And this we'll call this L3 and L4. So down here we got L1s, L2s. So let's go L3 and L4. Oops, let's back up there. L3 and then L4. And so notice how my scatter plot was on there. That all looks good. So if I now go to stat and hit edit, I now want to go over to L3, L4 on this one. So let me slide this over. I'm going to pause my video for a second and we'll graph this. So I've got this in. So again, if I want to graph it, I can hit second zoom. Whoops, not second zoom, just we'll put that. Just hit zoom and number 9. Notice that I've got a couple things going on this one. So let me turn off the first stat plot here. I think it's confusing it. So if I hit stat plot, if I choose number 1 and turn that back off, and I think I want plot 2 on. So that looks good. So let's try that again. Zoom 9. Still got a line going there. So let's clear that off there. Where that came from. Zoom 9. So there would be the graph of that data. So in this data, they were talking about, again, does exercise each week affect a person's GPA? Well, I would say based on this data, exercising and your GPA don't have any correlation whatsoever. So this would be considered a no correlation whatsoever based on this data. So we got that going on there. So it's a little tricky. Like I said, you got to pay attention. You can't have 2 stat plots on at one time. So that's why a lot of times we don't turn 2 on there, just to turn 1 on. But I didn't want to erase that data just yet. So I was kind of trying to hold off on that. Okay. So this next one, we have this Old Faithful one. So let's put this data into the calculator. Let's see what we got going on here. Construct a scatter plot with that. So I'll pause my video for a second here and we'll get this data into the calculator. So again, we have Old Faithful located in Yellowstone National Park. Is the world's most famous geyser. The durations in minutes of several Old Faithful's eruptions and times minutes until the next eruption are shown in the table at the left. Use technology to display the scatter plot to describe what type of correlation it is. So again, if I zoom and number 9, notice that we do have the scatter plot. And notice how it does look linear. And since as x is increasing, the y's are going up, we call this a positive linear correlation. So we have that kind of going on there. So what we're looking for in our data is how linear is it? So that's where we're kind of moving into is it looks linear, but how linear is it? So this is where we get into what's called a correlation coefficient. It measures the strength and the direction of a linear relationship between the two variables. The symbol R represents the sample correlation coefficient. And we have this formula here. And we're not going to use the formula. We're going to just let the calculator do this. So we're going to determine this value R. Now, the second thing we have is what's called the population correlation coefficient. It's represented by this P, and it's pronounced rho. So we're also going to be looking at that. Okay. So we're going to try to compare it to this population correlation coefficient. So some values for R. If R is equal to 1, this is considered a perfect positive correlation. If R is really close to 1, then it's called a strong positive correlation. So notice that this pattern here would be considered very strong. It's not perfectly linear, but it's moving in a strong positive linear relationship. Notice that if R is really close to 0, moving like 0.45, notice how this still has a linear relationship as x's are increasing, the y's are increasing, but it's more scattered. This is considered a weaker positive linear correlation. So we have a pattern here, but it's just not strong. It's weak. Now, if we go as x increases and the y values decrease, in this pattern, if R is equal to -1, this is considered a perfect negative correlation. Notice how if we have R is equal to something close to -1, like a -0.92, this is considered a strong negative correlation. Notice how the scatter plot is kind of tight together. But notice how this last one, the scatter plots ever, notice how we have like R is equal to like 0.04. Notice how that's really, really close to 0. Notice how that really has no linear relationship. It's kind of no really meaning between the two variables. So like here, they're saying IQ score and a person's height. There's really no relationship between a person's IQ score and their heights. But here it says the number of absences and your test grade. As your absences increase, your test grade seems to decrease. And I know, like with my experience with my class, if students aren't present, their test scores usually do go down. Here's, the number incorrect, an exam score. So the more questions you miss, so as the number of questions you miss increases, your test score decreases. That would be pretty strong. That's pretty powerful there. That's a perfect negative relationship. Notice how here it says income per thousands of dollars and the amount of spent on milk. That is not going to be a real positive relationship there, but we do know that as your incomes go up, you may be buying more milk, but that's not necessarily true. I would say there's probably more of a relationship between how many kids you have in your family. Kids seem to drink a lot of milk, so there's a more of a strong relationship there. Notice height in inches and shoe size. So notice how there is a pretty strong correlation. The bigger the taller you are, it seems like the bigger the shoe size you have. That's typically how it works there. Back to perfect positive. The number of adult tickets, movie tickets, the total cost in dollars. So the more tickets you buy, the more cost in dollars that goes on there. That would be considered a strong, or actually a perfect positive correlation. So we have these R values that we're looking at. So the R values are basically going to be between, R is actually going to be greater than -1, but it's going to be less than a +1. So the closer we are to 1, the stronger the relation is in a positive linear. The closer we are to -1, it's going to be a strong negative correlation, linear correlation. So using a table to test a population correlation coefficient P, or again, they use the word rho for that. So this is where we kind of have to use a table. So determine the number of pairs of a sample. So that's going to be our N. And we're going to specify the Lego significant. This is going to be given to us. So, 0.01, 0.05 are the most common ones. And to find this critical value, we're going to be using, to find rho, we're actually going to be using this table 11 in Appendix B. I think in your homework, they actually gave you this table, so you don't have to go find it. So the other thing is, to decide whether the correlation is significant or not, we have to compare it with the absolute value of R. The absolute value of R is always going to be a positive value. So we're going to be comparing R as a positive value. If it's greater than this rho, then the correlation is significant. Otherwise, there's not enough evidence to conclude that the correlation is significant. So if R is greater than the value that we find in the table, then there's going to be like what we call a strong linear relationship. Otherwise, we would say there's not enough information. That's how we kind of go about this. So it's going to be our conclusion. So then we have to kind of focus it around the actual claim. So what's the claim? So using table 11 for a correlation coefficient, in example 5, we used 25 pairs of data to find R. So we actually haven't found R yet. So example 5, I believe that's going to be the Old Faithful question up here. Where's Old Faithful at? This is Old Faithful. I think we had 25 pieces of data here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, this had 25 pieces of data. So to find R, we're not going to use this formula. We're actually going to use a calculator. So when we did our scatter plot, this was, I believe, our scatter plot for Old Faithful. Now, what I want to do is determine what R is. Now, to find R, there's a couple of things you have to do on your calculator. So one thing is you have to turn what's called the diagnostic sign. So there's this thing, let me make my calculator go back away. There's a little tip here to find R. Before using the TI4 plus calculator to find R, you got to go to the diagnostics feature. To turn on the feature, you have to go to the home screen and hit second catalog and move your cursor down to diagnostic on and press enter twice. So make sure it actually says on. So that's what we want to do with our calculator. So on the calculator, I'll go and make this a little bit bigger. Catalog is above 0. So to get to that, we hit the second button, hit the 0 button for catalog. Now, you can move your cursor down, but what I do is I hit alpha D twice, and that moves me down to the Ds. And then I just do my down arrow from there. And we want, instead of diagnostic off, we want diagnostic on. So we hit enter, and then we have to enter again, and then it says done, and that's taken care of. We won't have to ever do that again on this calculator. So that's been done for us now. So let's move back up to our question and see if we can make this work for us here. All right, get this working here. Okay, let's do it better. So in this Old Faithful question, to find R, what we do is we hit the stat button and we go to calculate and we do linear regression. That's number 4. Hit enter. Now mine's actually going to be a different list. Mine's L3 and L4, but typically you will just leave that as L1, L2. They usually don't have to change, but I'm going to change that to L3 and L4 because that's where I put my data at. And I think that's all we have to change. We don't have a frequency. Hit enter. Notice that R is going to be this 0.978, but see how there's a 6 there, that's going to be 0.979. So that's how we actually find R, is using the calculator. So again, I hit stat, went to calculate number 4. Usually there's nothing here you have to do except just go down here to calculate, because L1 and L2 should already be where your data is. And then the R value, which is considered the linear correlation value, coefficient, that's going to be 0.979. So notice how that's really close to 1. Okay. So that is really, really close to 1, 9.789. So notice how we had this 0.979, and I think that's what we had on our calculator was 0.979. So that's how we actually find R. So now what we want to do is we want to compare R. Well, actually, we want to compare the absolute value of R. So the absolute value of 0.979 is still going to be 0.979. And we want to compare that to the rho value. So to find rho, we actually have to use a table 11. So alpha is going to be this 0.05 and n is 25. That's about all we have here. So let's see if we can find this rho. Okay, there we go. So let me get that other piece up here. All right. So table 11 is over here. Notice that we need to know what n is and what alpha is. So in our problem, n was 0.0, or alpha was 0.05, and we have this 25 here. Remember, alpha was like the level of significance. So if we do that, 0.05 and 25. So 0.05 and 25, that brings us down to 0.396. 0.396. So rho is actually this 0.396. Now remember, if the absolute value of R is greater than rho, here we have 0.979. Is that greater than 0.3976? If that's true, then there is a strong claim here that this is a strong linear relationship. So that means the correlation is significant. So this means we have a strong, in this case, it's going to be a strong positive linear relationship, linear correlation. So we kind of pick up on that. So if I look at another example, maybe. So in your homework, you may come across a question like this. The accompanying table shows the ages in years of 11 children and the number of words in the vocabulary. So complete these parts A through D. So again, we're going to have, as a person's age increases, does their vocabulary increase or decrease, or is there no relationship between it? Well, I've got grandkids. I know that as they get older, their vocabulary seems to get stronger. So I would say there's probably a pretty good connection between age and your size of your vocabulary. But let's just see where this data plays out as well. So again, on my calculator, I'll go to stat. I want to go to edit. And again, I'm going to clear out L4 and I'm going to clear out L3. But for you all, you probably will stay with L1 and L2, clear out L1 and L2. But I'm not going to try to clear all this data because I still want to use it down the road here. All right, so let me see if I can slide this over. So the data we want to put in here are the ages and the vocabulary sizes. So I'll pause the video for a second while I'll get that data into the calculator. So I got this data into the calculator. So again, and person's age is 1 year old, they have a vocabulary of 7 words. If the person's 2 years old, they have a vocabulary of 250 words. And also if a person's 6-year-old, their vocabulary is 2,500. So there seems to be, as your age increases, your vocabulary seems to increase. There seems to be a strong correlation there. So let's hit the zoom and number 9, and it should create a stat plot for us, or scatter plot. Notice how this looks really very much so. This looks like a strong positive linear relationship. As x increases, the y values are going up. So now to find the value of r, if we go to stat, slide over to calculate, go to number 4. Notice how yours should probably say L1 and L2. Mine's L3 and L4. Hit calculate. It gives us an R value of 0.952. If I round it to 3 decimal places, 0.952. And since R is positive, and also how it's pretty darn close to 1, we should say this is going to be a strong positive correlation. So again, from our graph, as x's are increasing, the y's are increasing. So in other words, as the ages are increasing, the vocabulary size is increasing. We kind of see that relationship. And since r is close to 1, we kind of base that. So if we look at our next question, what is r telling us? I'm looking for as age increases, in other words, the vocabulary tends to increase as well. I'd be choosing E in that sense, because that's what we're kind of seeing from the R value and the scatter plot. So the other thing is, just how strong is this? So if we use the Pearson correlation, so again, that's that rho, that P value, we can kind of compare that to the R value. So remember, if the absolute value of R is greater than this rho, there is a strong relationship here between the data and a linear relationship. So in our example here, to find rho, we need to know the sample size is 11 children, and alpha is 1.01. So that would give us this 0.735. So notice how rho would be 0.735. Our R value was 0.952. So is 0.952 greater than 0.735? Yes. So we are seeing that there is a strong linear relationship there, and it's going to be a positive one. So I would say there is a strong correlation or strong positive correlation with the data. I should say strong positive linear correlation, since we are talking about lines at this time. So the thing is, we have what we call hypothesis testing. Right now for us, remember how we have the null hypothesis and alternative hypothesis. What we're going to focus on in this unit is just this. We're just going to be focusing on this two-tailed hypothesis. So remember, a two-tailed hypothesis, we're going to have this curve, normal curve. In a two-tailed, remember, we're going to have a half alpha over here and this half, can't make it alpha here, and a half alpha over here. Because you remember, alpha's got to be broken apart into 2 pieces. So if I do a two-tailed, I have to use these half alphas. So again, to find this t statistic, we have this formula here that we can find the t statistic. Or again, we're going to just use the, on your calculator, we're just going to use inverse t. So I believe we can find that under the distribution area of our calculator. So we're going to do that instead. Now, to do our test statistic, though, notice that our degrees of freedom actually has to be this 2, n minus 2. So, that's something else we have to pick up on, is the degrees of freedom is actually going to be not n minus 1. The degrees of freedom is going to be minus 2. So let's see if we can pick up on this here. So in hypothesis testing, again, we have to identify the null and alternative hypothesis here. So from there, we want to identify alpha. The degrees of freedom is going to be this n minus 2. Now, we can use this table, 5, or again, we can use inverse t on our distribution. Now, to find the test statistic, though, we can do this here, but we're gonna do a different spot there on this as well. We're not gonna use this formula. We're gonna kind of take a shortcut there. So we're gonna kind of avoid the tables here. We're gonna find this test in our graphing calculator. So again, if T is in the rejection region, then we reject the null hypothesis. If it's not in the rejection region, then we fail to reject the null hypothesis. And then we're going to interpret the decision in the context of the original claim. So we have these formulas, but again, we're going to see if we can kind of do some of this math with the calculator. So let's see what we got going on here. So the number of hours 10 students spend studying for a test and their scores on that test are shown in the table. Is there enough information to conclude that there is significant linear correlation between the data? So 10 students studying for a test and their scores on that test. So as their hours increase, do test scores increase as well? Do you think that would be a relationship there? Do you think studying impacts a test score? Right now, I'm thinking, yeah, there should be probably some type of relationship. But the question is it linear? So let's take a moment and we'll put the stat into the calculator. So we hit stat button, number 1 for edit. Again, I'm going to clear out L4 and I'm going to clear out L3. And then I'm going to put that data in there. So I'll pause a minute and get that data into the calculator to see where this takes us. So again, we may not have had to actually put this data into the calculator. I was just kind of curious to see what it looks like. So if I hit zoom in number 9, notice that it looks like it's going to have a strong positive correlation. So I'm looking like there should be a really strong R value here, just based on this. So let's see what we got to do in our problem here. So the hypothesis is we're going to have this H sub 0 and H sub A. So the question is, how do these play out here? So, so we have H of 0 and H of A. So H of 0 is going to be our alternative one, and notice how it's going to be, does not equal. And H of A is, I'm sorry, the null hypothesis is always the equality. So we have here, we have the equality and the not equal to. So that's what we're kind of going to be doing are those. So let's see what, let's set up here again on that. So we're going to say rho equals 0, rho does not equal 0. So this is going to be our p-value, if you will. So if the p-value is equal to 0, then we're going to say no significance. No significance whatsoever. If p does not equal 0, then there's going to be significance. But I guess the question is how much significance is going to be present there? Let's see what it says up here again. So there's going to be a significant correlation, but how significant will it be? Remember, it's going to kind of play out here as we move forward here. So the level of significance is going to be this alpha. Alpha is going to equal this 0.01. So our critical values are now what we want to pick up on. So our critical values for the rejection region, this is going to be our negative t sub 0 and our t sub 0. So again, we're looking at these t values. So remember, if I'm using the normal curve, the negative t sub 0 and the t sub 0 are going to be here and here. What we pick up on is in a right-tailed, we have to be right of t sub 0, and you have to be left of negative t sub 0. And remember, we have to actually use half of alpha. Use half of alpha over here. So remember, there's symmetry with respect to the t values. Now to do this, notice that we have to actually use 1/2 alpha. So we actually got to go 0.01 divided by 2, which would actually be 0.005. So we have that going on. So if we use our calculator on this to find these critical values, remember, we can do that under the distribution. So if it's second distribution, number 4, let's go up again. So second distribution, number 4. So the area is going to be actually the 0.05, 0.005. And the degrees of freedom, remember, that's going to be n minus 2. So if we were doing 10, n minus 2 would actually be 8. So if we go back to our calculator there, we have to actually use 8 there. So this will give us our t sub 0. So we get this negative 3.35 or negative 3.355, if you will. But also we have 2 values here. So t sub 0 is also going to be 3.355 because of the symmetry going on there. So that would be our rejection regions to the right of 3.355 and to the left of negative 3.355. So our test statistic to find that using our calculator is going to be, we're actually going to use stat and go to test. Now, the test, we're looking for something. So that's how we have this linear regression t-test. So that's actually F. So linear regression t-test is what we want. If we hit enter here, again, I'm using actually L3 and L4. You're probably using L1, L2, L3, L4. And notice how we have that does not equal 2. And if we come out here to calculate, that's how it gives us our t value, which is going to be this 9 point. So let me bring that back over here. So our t value is going to be this 9.341. So 9.341 is going to put us to the right of this 3.35. So that's going to tell us to reject the null hypothesis. So the null hypothesis means, like I said, no significance. That means we're looking at the alternative hypothesis, which means there's a significance relationship here. So the interpretation is then there is significant evidence of a linear correlation. And also, I mean, just to the graph, we kind of picked up on that as well, that the graph also kind of verified that. But here, notice how we actually can kind of avoid doing the stat plot, if you will. Not actually, we had to still put the data in, didn't we? It still came from the L1, L2. So we still had to put the data in to get that. So we didn't get the way that easy. So that's how it does give me the degrees of freedom is 8. It does give me some other information here that may become useful to us as we move forward. There's also a down arrow. There's more information to be had. Notice how it does give me my R value here as well. So actually, I can get my R value from this spot as well. I don't have to do the other area. I can actually just do this spot for the R value. This 0.957 will come from there. So there's a couple of places to get the R value. This is another location doing the test, the linear regression test. Okay. So let's see if we have one more example here. Notice that we also have the table. Instead of doing notice how here I found negative t sub 0 and t sub 0 using the calculator. But notice how, again, we had this 0.05 and we had degrees of freedom was 8. Notice how we have 0.05 degrees of freedom. That would give us this 3.355. Remember, if it's two tails, a 0.01 could also be used, and that would still give us this 3.355 if we looked at it from a two-tail perspective. So one tail would be 0.05, but two tail would be the 0.01. So we got that going on. So one last example. So in example 4, we use 10 pairs of data to find R, test the significance of this correlation, and alpha would be 0.05. So in this example here, we have the GDP numbers here. So let's see if I can find that anywhere. So if we go to stat and edit. So notice how my L1 and L2 are those numbers there. So I'm going to clear these off here. Say goodbye to these guys. So those were our things there. So notice that we have that in our calculator already, so we'll come back to that. But remember how we let me see if here. Let's come on back up here. So remember, if I go back to my stat plot, if I turn back 1 back on, so if I go to y equals, it's probably quicker. Turn on plot 1, turn off plot 2. If I go back to my zoom number 9, notice that was my data from the GDP question. And notice how it looks like there is a relationship there of it being linear. So the question though is, if we want to look at our hypothesis testing again is going to be, H of 0 would be rho does equal 0. And the alternative would be rho does not equal 0. So remember, this has no significance. And this means significance if we're doing a hypothesis testing on this. So to do the hypothesis testing, one thing we need to know is what the curve is going to be is this you have to forgive me, I usually don't do this because I'm so rough at it, but notice how these are going to be two-tailed. So negative t sub 0 is going to be over here, and we're going to have this t sub 0 is going to be over here. This is our rejection region. So one thing we have to find is, t sub 0. So notice that if in the two-tailed, this is going to be 1/2 alpha. This is going to be 1/2 alpha. So if alpha is going to be 0.05, we got to do 0.05 divided by 2. So if I can quit that, 0.05 divided by 2, that's how we get this 0.025. 0.025. So if I use the calculator, I can use the inverse t, that's a distribution. So if we go to second distribution number 4, we change that to 0.025. And the degrees of freedom this time is still going to be 8, since we had a 10 there. We're going to have to use n minus 2 is the strategy there. And we hit enter, and we get this negative 2.306. This is going to be negative 2.306. This is going to be 2.306. So now to find, the test statistic, instead of using the formulas, we're going to use the calculator. If we go to stat, go to tests, and we're looking for linear regression test statistic, I think it's like F, linear regression t-test. So this t-test here, if I hit enter there, I got to change this back to L1, change this to L2, and we got that already set to not equal to 0. if we calculate, this gives us our t value. So that's how the t value is going to be 5.078. Notice how that is going to be to the right of, it's going to be in the reject region. So that's kind of what we're concluding, because it looked like it was going to be linear. Excuse me. So we would reject the null hypothesis. And remember, by rejecting it, we're saying there is significant evidence to see a linear relationship there. So there is evidence. Excuse me. Or a significant relationship there. Well, my voice is gone. I hope you can get some out of that. Have a good day.